Yeah, good evening. I am from NTPC St. Alok Gupta. So good evening to all my panelists, my colleagues from EPRI. Welcome to this CII Summit for your presentations. And I also welcome all the attendees to this virtual power plant summit, all the delegates. This session is on by EPRI. This is having an international flavor. So we have our colleagues from EPRI. As we all know, EPRI is a premier institute doing research and development work in the field of power. And if you have a look at the tagline of EPRI, the tagline says, "Together we will shape the future of electricity." And EPRI membership essentially consists of the premier utilities in USA and across the world. NTPC in India also has subscribed to 3 programs of EPRI, one being on steam generator, other being on turbine generator and coal quality impacts. EPRI essentially is trying to create an awareness on power generation delivery in a safe, reliable, affordable, and environmentally responsible manner. So with this brief input about EPRI, I would like to simply touch upon the topics which will be covered in this session. We will be covering the flexible operations. I think Mr. Storm will be covering the flexible operations from where Mr. Banerjee and VGB speakers left. There will be coverage on emission control because, as we all know, that emissions are very important, and particularly when we go for flexibilization at part loads, emission control becomes a challenge. Another challenge which we are all facing in the power sector, particularly in coal-fired generation, is about how we can have control on greenhouse gas emissions. So our speakers will deal on carbon capture and storage. As more and more RE is getting integrated into the grid, it is essential that we have more storage. So we will have speakers who will be speaking on the latest trends in energy storage. I presume the focus of discussion will be on batteries, will be on pumped hydro, and will be on compressed air storage. So we have a very enchanting session lined up for all the delegates. So I will not stand between the speakers and the delegates. The first speaker will be Mr. Stephen Storm. He is the Principal Technical Leader, EPRI. And in fact, he has been associated with NTPC also in this technical minimum and ramp rate, how we can cope effectively with that. He is into plant performance improvement programs for the past 2 decades, and which includes combustion optimizations and complying with the environmental requirements. I think, Mr. Stephen, you can start your presentation. Over to Mr. Stephen Storm.
No issues? Can everybody hear me okay?
Yes, perfectly.
All right, fantastic. So I was asked to give a presentation on best practices for managing thermal and flexible operations. If everybody else could just mute theirs, that'd be great. So I'm going to get started. Let me go ahead and advance the slide. So Mr. Gupta, thank you for the introduction to EPRI. Just as a kind of a general introduction, as Mr. Gupta said, EPRI is a research organization, and our focus is on developments relating to generation, delivery, and use of electricity for the public benefit. So our core mission is around driving safe, affordable, environmentally reliable generation. Also, as Mr. Gupta said, you know, EPRI is an international company with a global impact. So EPRI members represent about 90% of the electrical generation in the United States. And I believe we're over 40 countries worldwide now. And then also another important note to make in regards to being an international global research company is that greater than 40% of our funding comes from outside the U.S. So today my focus is on kind of sharing some of the work that we're doing in the role of flexibility and heat rate optimization. So a lot of the work that we do in the future is going to be based on the work that we've done in the past. When you're looking at thermal efficiency and optimization, a lot of the actions and the efforts that CNPEEP and NTPC and other organizations in EPRI that I've worked with in the past still apply, but we've got to simply work smarter and not harder and find ways to be able to, utilize the lessons that we've learned in the past as we drive the future going forward. So in regards to flexibility, EPRI has been studying flexibility for the past 40 years. And anybody who's a member of EPRI knows that in 2021, we actually have some new programs that are going to be a part of our generation portfolio. And so one of those new programs is a program itself on flexibilization as well as heat rate optimization in our 223 fleet optimization strategy program. So I want to share some of those visions for, how you apply that and towards best practices for heat rate and flexibility. So there's three different core areas that I think are critical for India and anywhere around the world in regards to how you manage a heat rate and flexibility program simultaneously. And that's where you have to utilize and leverage strategies that we've learned in the past, online real-time monitoring presentations. We had some great speakers talking about digitalization and the transformation and how technologies have been applied to work management and thermal efficiency improvements in the past. And so how we drive that into the future, we need to take those same tools and strategies into how we manage flexibility and how we conduct assessments, how we apply best practices, and how we drive that into our overall strategy for fleet optimization. Two of the major trends that demand optimization in regards to flexibility, as we heard in the opening speeches today, over 370 gigawatts of total generation in India, majority of that being subcritical, supercritical coal generation. And so we've got to be able to sustain that fleet, and we've got to learn to become more adaptable to meeting the mission profile demands for what the grid, what it takes to keep the grid stable as we continue to integrate more variable renewable energy into that grid. So what that means is that we're going to see a lot of the older plants and even the new plants either in reserve shutdown or cycling, and in some cases two shifting, which is going to drive capacity factors down. Typically the heat rate trend is as we drop down below 50% MCR on our operations and our capacity drops, you see an exponential decline in heat rate. And so how you manage heat rate degradation and what's your strategy around optimizing efficiency under flexible operations is a key area of research that we're focused on. But the other side of the coin is that as you have more startups and shutdowns, the more it's going to likely impact your EPOR. So as we continue to advance new generation and drive new technologies, I think it's important that we understand these two main trends that have to be adapted to make sure that we've got a sustainable fleet going forward. For the past 2 decades, I've been engaged with the Indian marketplace and worked with NTPC extensively on CO2 reduction programs through other DOE initiatives or past USAID initiatives. And I'll say that those same principles that we've applied over the past 20 years, whether it's applying the essentials of combustion optimization or heat rate essentials on how you manage a heat rate program and how you track boiler losses and turbine cycle losses are still important. We just got to be able to understand how we do that now in a flexible manner. So I think one of the key points in managing heat rate and flexibility simultaneously is to understand how to track those losses and how to track those key performance parameters in regards to both efficiency as well as flexibility. And how you do that needs to be applied into a systematic approach. So over the last 40 years, EPRI has worked diligently to drive a systematic approach towards flexibilization. And that approach is complex, and it is time-consuming process that demands collaboration. So kind of as Mr. Banerjee shared in the last presentation, the strategy that I have proposed to India to be able to drive improvements in regards to flexible operations is to really focus on the core fundamentals of flexibility. So those core fundamentals, represent the integration of training and awareness, how you apply the operations and best practices to the fleet, what types of systematic program management efforts are required, and then ultimately what your defense strategies are going forward, and how you apply those strategies is really how you drive the culture of people. And so opportunities and events like this event is an opportunity for me to kind of share that approach. So as we go forward in 223, I think one of the key important deliverables will be to continue sharing a database of information from past lessons learned, continuing meetings and webcasts virtually. We're finding that this is the new normal. And then also making sure that we have the latest technologies and best practices being presented in both our flexibility conferences and our annual heat rate improvement conferences that are instrumental to the EPRI portfolio. So another area, something that we've discussed widely in being able to drive those best practices, I think, is using technology and platforms to disseminate those past lessons learned. So some of the areas that we're looking at expanding in P223 is a flexible generation video series that kind of helps visually understand what the challenges are with flexibility, what that looks like in regards to how you adapt to those changes, and most importantly, making sure that industry understands what the precursors to those damage mechanisms are so that you can help balance and offset the potential implications of flexibility, as you experience more challenges like thermal fatigue and layup corrosion, how you manage heat rate degradation, common operator challenges, and when your units are offline, how are you managing your layup strategy and your balance of plant O&M? So you've got to have a asset management offset strategy that looks into 4 key areas in regards to measurement, knowledge transfer, and then process optimization on applying these strategies to help offset potential damage. But to do so, you also have to have a set of guidelines and templates. So another key focus of flexibility should be to have anybody who's operating a fleet of generating units should have a flexibility program in place and a set of guidelines that basically helps you successfully manage that fleet and manage those assets, taking the past lessons learned as we continue to drive the future with state-of-the-art technologies that my colleagues are going to present in the next sessions, as well as some of those that were discussed earlier with the DOE Coal First initiatives. So then that brings us to benchmarking assessments and measurements. So if we want to benchmark and manage our assets from a flexibility standpoint, I think the real key is integration of people, process, and technologies, and taking that systematic approach, applying it to how we hit those core 4 components towards achieving resiliency, asset flexibility, and most importantly, ensuring viability of the flexibility so that we can drive those key flexibility attributes towards a fleet and make sure that we are taking those lessons learned, applying that. So one other area that we've been working hand in hand with NTPC with as a true industry leader is to develop a set of benchmarking templates for conventional steam generators. And it's essentially a platform where we can collect information in a timely manner, have a guidance document, a set of standards of performance, and integrate that into our defense strategy to understand how good of a job that we're doing on managing flexibility, whether it's at a unit level, a station level, a fleet level and or globally in regards to the overall session. So it's important for me to also acknowledge that that this work is a U.S. DOE project supported under the Power and Energy pillar under the India Strategic Energy Partnership, which is co-chaired by DOE's Office of Fossil Energy and Industries, India's Ministry of Power. So I'll kind of give you a quick overview of what that set of templates look like. So right now, we're building a set of templates that includes 10 different templates for 10 different areas of subcritical and supercritical generators that has a process for risk management on taking those lessons learned that we've identified through past work that EPRI has done through the Missions Profile Working Group and through many decades and years of research. And then we're integrating that into 4 core areas in regards to those conventional steam generators. So that's focusing on the boiler, the turbine generator, the balance plant, and environmental controls. And so what we've done is we've separated those 4 core areas into 10 templates to really focus on how you digest the complexity of flexible operations and how it impacts nearly every part of a conventional steam generator. Whether you're talking about the controls, the operating mode strategy, the O&M best practices, or even the cycle chemistry and balance of plant. So it's important that we understand that these are critical. So right now, the current status of the tools that we have over 615 line items of key lessons learned that we have integrated into these flexibility templates, where you have an opportunity to put a weighted value on different component areas that need to be addressed. When you do an annual assessment, you can classify that, and then ultimately it's a opportunity, a tool that helps scorecard your performance in regards to flexibility. So when it's all said and done, to be able to manage a fleet's flexibility, you can identify potential gaps or degradation in certain key areas so that you can understand where you really need to prioritize your resources and your teams to become more flexible, and how you can mitigate some of those damages or precursors to damage mechanisms before they become a more significant problem. So it's essentially a tool that has a multi-directional purpose. The flexibility tool can be used for risk management. It can be used for driving awareness for assessments, but most importantly, it can also drive project developments on areas that need improvement, as well as in-depth flex studies, or application of digital solutions to where you could take those variables with pod process signals and values and diagnostics back to an M&D center so that you can monitor flexibility in real time. And so if you integrate this approach of applying standards towards people, process, and technology, you can drive this into your risk mitigation strategy along with a database of information over time that supports the EPRI mission, which is also the mission of most utilities and generators that I've ever worked with, is to generate, safely, reliably, efficiently, and environmentally consciously. And then you can take those lessons learned as standards, prioritize them, and then drive that into your future project developments or future research that you take forward. The 4th quadrant of the core 4 fundamentals of flexibility is application to defense strategies. And this is where technology and process optimization comes into place to help us take our aging fleet of many of the units in the U.S. are over 40 years old on conventional steam generators, and there's many older units in India too, with some uncertainties on whether or not they're going to operate for 5 years or another 25 years in operation. So if you want to operate flexibly with an extended amount of life, you've got to take a look back in time. And I'll just share you a scenario here of GADS data, where we took a look back at 35, 45 years of data of units that had 40 to 50 starts per year that were operating under a very flexible operation scenario. And you can see that the boiler is where you'll see a number of the potential damage mechanisms that are going to appear. and this is also my experience over the past 2 decades. So, implementing fundamental approaches to that, lessons learned based on how you manage thermal fatigue, where the critical thermocouples are, what are those critical temperature differentials from side to side, from left to right on major components, what is the protection systems that you must implement and maintain to be able to preserve performance, and all that for a given set of standards of performance that are taken into account material temperature ratings and heat transfer and velocities and circumstances that may relate back to a site-specific challenge. So, for example, in India, how you manage a component and ash deposition and flue gas velocities is critically important for mitigating erosion. And so as we do that more flexibly, the standards are going to change. So I think, as you go forward, it's important that our operations and maintenance teams understand not only the component temperature limitations, but also the material limitations. And then some of those KPIs that we've got to take into account when you're doing life expectancy evaluations on how you sustain this fleet going forward. So that might integrate things like superheat and reheat outlet thermocouple headers, making sure that we're maintaining those economizer temperatures on headers, and or pad weld thermocouples on superheat and reheat outlet headers as a low-hanging fruit, cost-effective approach to, managing those pressure part and components. But the key is to work smarter, not harder, and to manage your data and information through opportunity assessments, whether it's through a static approach, like we're developing with the benchmarking and assessment tool, or what we do in real time and how we take that data and information back to a monitoring center and how we use that into a more dynamic optimization program, whether it's in our controls or a controls optimization scheme that is closed loop, that's looking at the systems holistically, and not only efficiency and not only heat rate, but also overall holistic optimization of the environmental controls performance, as well as the reliability of the unit is important as we work together and shape the future of electricity. So I know time is limited, so I will stop there and I will stop sharing my screen, Mr. Gupta. I'll give it back to you.
Thank you, Mr. Storm, for your presentation. I think many of the delegates would have been looking for solutions from you in terms of step 1, 2, 3, 4, 5, 6, how to improve the efficiency. But EPRI has once again demonstrated that solutions to complex problems is a long process. It's a process. So you have introduced us to the different templates and the collaborative working which all the individual utilities have to do, and there has to be a database, and with that database we will jointly arrive at what will be the solution. Thank you very much, Mr. Storm, and I think our participants will ask the questions at the end of the session. Now we move forward. We will go to the second presentation. It will be by Dr. John Shingledecker, and he will be focusing on R&D considerations on materials for advanced generation. And his brief intro, he is a senior technical executive in EPRI, and he has been leading key technical projects in materials and manufacturing for new advanced emerging generation technologies. His current research is focusing on nickel-based structural alloys for various generation technologies. So I will not take much of your time. Can I ask Mr. Dr. John Shingledecker to start his presentation? Over to you.
Thank you very much, Mr. Gupta, and thank you for the opportunity to talk to everyone today. Steve laid a nice big picture for the power plant. We're going to go a little bit more into some of the technical details around materials. And I think if there's one message I want to leave with those on the phone today is that materials and metallurgy in particular are critical to achieving, world-class performance in the power plant itself. And the way we look at this within EPRI is we actually have a materials program, and because of this, foundational nature to metallurgy, to all sorts of things. And so if we think about the life of your power plant, whether we're going to put it through a flexible operation mode now or in the future, it starts with what you have in the plant itself, and that goes back to how the materials were specified, how the materials were fabricated, what type of degradation modes are going on in the power plant. And then when it comes to managing the life, a key tool in your toolbox is actually repair. So our materials program really focuses on materials and repair, because repair technology, often welding, is really a critical aspect to managing the life of those plants and achieving performance as you address the changing operation profile that you're going through. So what I'm going to highlight today is just a few areas that are specific to the global issues, but very specific to India. I've been to India over 7 times over the last few years, mainly working with NTPC on various challenges in the area of advanced steel metallurgy for existing supercritical and ultra supercritical power plants, as well as looking towards the future for higher efficiency, lower emission power plants and things such as advanced ultra supercritical technology. So we'll touch on a few of those in the presentation today. As a little bit of background, and my colleague John Seifert manages our new program 229. Those who were involved in India before know program 87, the materials and repair program. And really the fundamental reason for this program's existence is to transfer materials technology into utilities. And that can be in the area of things such as best practices for material selection, fabrication, guidance, welding, and repair. We do a lot of work on failure investigations and a databasing of failure analysis so that we can inform appropriate root cause and corrective actions. And the team that we have at EPRI, not just myself and John, but a whole range of experts in the area of corrosion, high temperature metallurgy, advanced steels, etc., is really a value to I believe the entire industry. I'm based out of our EPRI offices in Charlotte, North Carolina, where we also house quite a number of laboratories. So for those who are perhaps familiar with EPRI, we know we do a lot of our research with a number of collaborators, and collaboration is a key aspect of our research, and we are able to bring the best and brightest from around the globe. But often the best and brightest are actually in our labs, and in particular in Charlotte, we've invested tens of millions of dollars in the last few years to upgrade and continue to keep our labs as state-of-the-art. And materials is a cornerstone of that investment in the area of high temperature mechanical testing, of welding and repair technologies, of advanced characterization, as well as our ability to do field simulations with our large high bay. So getting into it, the backbone of the ultra supercritical fleet, the newest and most advanced plants that India is operating today, are what we call creep strength enhanced verdict steels, and in particular grade 91 steel. There are others, grade 92, etc. And this material achieves tremendously good properties, high strength, good resistance to fatigue, etc., when it is properly fabricated, welded, heat treated. However, the control in the fabrication, all starting at the melting practice of the metal all the way to the field post-weld heat treatment, has to be rigorously controlled. And if it is not, you can lose substantial performance. Over 15 years of research in this area, we have a publicly available guideline which everyone should download that covers the key things you need to know about the manufacture and construction of grade 91 steel. And you can see here, you'll have those who attend. I'll have access to PDFs at the end. You can go to EPRI.com and type in that link. But just as an example, this plot on the bottom is a Larsen-Miller plot, and this is a way to represent life, high temperature life, as a function of stress. And basically, if you look at these black data points, this line right here, which I'm highlighting, this is the performance of the material that's used to set the code stress allowables, the size of your components. By virtue of having a weld in the material alone, you get a degradation in strength. And while it may not be apparent what that degradation in strength is, you can actually lose a factor of 10 on life. So if you put a weld in a specific stress orientation, you may see up to 10x reduction in life of that component. If you improperly heat treat grade 91 steel, you may get to this lower bound curve, which can have between the highest performing material and the lowest performing material almost a 200x difference on life. So a component that would have lasted over 1 million hours may not even last 5 years in your power plant. So it becomes critical that you take into account these aspects as you continue to build more power plants, and as you begin to manage the life of your existing power plants. Knowing what material you have is absolutely critical. Because of the need to repair materials like grade 91 steel, we have spent an enormous amount of effort understanding the metallurgy of grade 91 steel and welding repair. Typically, and you saw in my example before, that improper post-weld heat treatment may reduce life by an order of 200x. We have worked to develop processes and procedures that do not require post-weld heat treatment. These have been codified in the National Board Inspection Code as Welding Method 6 and Supplement 7. And these techniques are now being used globally. We know of some limited instances even in India, but we know of instances around the globe, and in particular in the United States, we've documented over $10 million in savings a year for some members using these techniques that don't require post-weld heat treatment. It's risk mitigation for improper heat treatment as well as reducing the outage cycles. So as a tool in the toolbox, innovative repair strategies can save time and money and actually increase safety when done properly. And we have a lot of guidance in this area. And so this is an area that really should be on the forefront of the mind as you're operating supercritical power plants. Some of our ongoing research, which I think is very useful to the Indian audience, is the advanced stainless steels. So the superheaters and reheaters, I think Steve showed a very brief clip. As you get to higher temperatures, no longer can you use the CSEF steels in the reheaters and finishing superheaters of these supercritical units because the temperatures have gotten so high. And so these steels undergo metallurgical changes with time. And while we have legacy documents on the guidance for traditional stainless steels like alloy 304H or 347H, there are many new materials, Super 304H being one of the key ones, HR3C and 347HFG being the others. And these materials, if need to be understood in challenges that have been encountered in many plants around the globe with steam side oxidation, the failure of dissimilar metal welds, out of service stress corrosion cracking, and then as we're showing in this image here, long-term microstructural degradation. And it shows the complexity of the structures and the formation of deleterious phases. In this case, these small little yellow dots that you may see, or these blue regions that you may see in these images, represent phases which form only after long-term service exposure and how they affect properties. So we build up tools like our Atlas of Oxide scales and our welding guides, and we use this fundamental data to inform life management decision-making. Finally, another area that the U.S. has experienced is we've had a rapid growth in the use of forced oxidation wet scrubber technology. And in following this talk, we'll have my colleague Tony Facchiano talk about that in more general for emissions controls. But one of the challenges that the U.S. faced, the U.S. and North America faced when they implemented FGD vessels was the materials of selection. Quite frankly, they did a very poor job of selecting materials, And because of that, we had a widespread corrosion issues in our FGD fleet. Over 160 FGDs stalled in only a period of less than 10 years. And through a detailed root cause investigation and extensive field testing campaign, where we actually built mini scrubbers in the side of scrubbers to actually perform laboratory type tests, we were able to produce new material selection guidance. Beyond that, we're working now with our members to optimize performance. So we've developed test methodologies and new methodologies for assessing the materials in the current state, because every FGD has a very unique chemistry. And so we're now getting to the very details of optimization of these FGDs for mitigating corrosion, minimizing water usage, that sort of thing. Materials, as I said, are foundational. And so as we look to advanced ultra supercritical power technology, which India has a large national program, NTPC BHEL, working together to look at 700 degrees C plus plant, they no longer can rely on the creep strength enhanced ferritic steels like grade 91 and grade 92 for pressure parts. And so using this kind of 100 MPa line as a criteria, you can see that that's the reason that we're stopping around the 600 degrees C mark for current supercritical technology. To move to the future, we need to use things such as nickel-based superalloys. And EPRI has been involved as the technical lead for the U.S. Department of Energy's program for advanced ultra super that has developed the materials technology to enable AUSC. Our current ongoing work in the area of AUSC, building on that 15 years of foundational materials research, is a demonstration activity around around various key components in the AUSC. So we call it the AUSC component test or COM test. And you can see some of the things that we're doing. We're building a large header assembly, we're demonstrating large castings, and we're demonstrating large forgings. And so this is really to build out the final pieces of the supply chain to enable AUSC technology. Finally, as we look to even further into the future, we look at there are many new technologies on the horizon, and materials and the AUSC materials technology is foundational to those. So these can be things such as supercritical CO2 power cycles, concentrating solar power plants. There are new manufacturing methods now coming on board, like additive manufacturing or 3D printing, as it's sometimes known, as metals. All these technologies require an in-depth understanding of the materials and the selection to properly enable, more advanced technology in the future. So we have a lot of ongoing work in these areas to really support and shape that future of electricity, as Mr. Gupta mentioned right at the beginning of the talk. And so the materials really cross-cuts from the current life management of plants to future advanced technology. And just to give you a flavor of what we're doing in our research today, if it's of interest to you, we continue to work on advanced steels. Advanced steels did not stop with grade 91. There's now grade 92, there's grade 93, there's some new Thor 115 and Super VM12. All these alloys, many of them have never been independently vetted by anyone other than the manufacturer. So EPRI is doing a lot of research to look at these materials and understand the behavior of welds, understand the behavior of multi-axis creep damage, looking at innovative repair approaches for these materials. I mentioned already our work at advanced stainless steels, and we have a lot of tools to help utilities enter this technology. So with that, I'd like to wrap up and move on to our additional talks. So thank you very much, Mr. Gupta, for the time.
Thank you, Dr. John Shingledecker. I think you have given us a very good flavor regarding the appropriateness of the materials which we select for our supercritical and ultra supercritical boilers. Reliability is very, very important for all these ultra supercritical and supercritical boilers, and materials not only they withstand high temperatures and high temperatures give us efficiency, but reliability of these materials is also very, very important. You have very rightly said that grade 91 steel is the key. Super 304H is the key, and in some of the plants in the Indian part sector, we have faced exfoliation problems. We have also found indigenous solutions to deal with those exfoliation problems, but that is a problem in T91 exfoliation. One advance warning I think you have given to the Indian power sector regarding proper material selection for wet FGD. I think we need to look into that, because India is going in a big way for wet FGD. In the coming years, we will have wet FGD in most of our plants as a prerequisite of environmental compliance. And I think we need to relook at whether the appropriate material selection has been done. Future in material science belongs to the nickel-based alloys. Additive manufacturing is the new destination. And I think the crux of your presentation was probably that we need to pay a lot of attention to material specification, the manufacturing, the fabrication, the heat treatment, the welding and repair. If we want reliable working of our powerhouse, then both in boiler and turbine, we need to have reliable materials. And materials failures can be very costly to a utility. Thank you very much for your enlightening presentation. And now may I request Mr. Anthony Facchiano. He will be talking about emission control. And Mr. Anthony, emission control will be a big challenge with flexibilization and part load. And I presume that you would be focusing on those aspects. Over to you, Mr. Anthony.
Yep. Yes, I will. I have to upload my presentation. I am now the presenter. I can do that. Or is it uploaded for me? Is my presentation uploaded, or do I need to do that myself?
May who upload the presentation?
So you will have to upload it too.
Okay, I'm now the presenter, and I can do that. Hold on a second.
Yes, sir.
I will do so. Okay.
Okay, sir. Okay.
Okay, here we go. Okay. Can you see my presentation?
Yes, Mr. Anthony. We
Okay,
can
thank
see.
you. Thank you. I got the thumbs up from Steve Storm. Thank you very much, Steve. That's what I was hoping for. I want to wish everyone a good afternoon. For me in California, it's actually very early in the morning, but good day to everybody. I am honored to be here today. I am Tony Facchiano, and I am the Senior Program Manager of Effery's Environmental Control and Combustion Program. And with that, let's get started. Okay, hold on a second. Where? Okay, so here's the overview of which tells the overall mission of Effery's environmental control program. And we talk about an integrated approach. There's a few things to keep in mind. One of them is it's not just about cleaning the flue gas that goes out the stack. Okay, it's also about what we send to the water, what we send to the land, and the product use. And it all has to be looked at in an integrated fashion. In addition, we have to look at a integrated approach or a holistic approach to all emissions of concern. For example, in the boiler, in the combustion process, if one has a problem with CO or high levels of sulfur trioxide or unburned carbon and ash, and the solution may be to increase the excess air, that may have downstream consequences on the FGD or on the SCR, or certainly on heat rate. So we need to look at things, we need to approach this in a fashion that looks at the process holistically, considering not only emissions, but the impacts of what we're doing to control emissions on the plant reliability and the plant performance. So we need to keep that in mind. So we always start with the combustion process, okay? And when we talk about the combustion process, the main, from an environmental control perspective, the boiler is where we minimize the formation of emissions. Everything downstream of the boiler, what we're looking at is cleaning up or capturing the emissions that are formed in the combustion process. So if we minimize those emissions in the combustion process, we're making things easier for all downstream environmental control equipment. A few things to point out. Low NOx burner, low NOx overfire air, low NOx methods of operation have been with us for some time. But the focus now is what are the consequences? Again, the holistic approach. What are the consequences of a low NOx mode of operation? And it's very much fuel quality dependent. And looking at Indian coals, very high in ash. So some of the issues we're dealing with is ash deposition, which is detrimental to heat rate, to furnace exit gas temperature, to the entire operation. That needs to be controlled. Fireside corrosion as well. And then finally, if you look at the curve, the graph at the bottom of the chart in the middle, that tells the story of what we're showing here is on the x-axis air-fuel ratio. On the y-axis, we're looking at specific different combustion parameters. And what's shown here is if we increase the air-fuel ratio, or in some cases the level of staging for NOx control, we can get a reduction in NOx. We can get a reduction in SO3, and we can get certainly an increase in efficiency. But it leads to other issues. And, for example, that would be detrimental to the unburned carbon and ash, to the ash deposition problem, certainly to fireside corrosion. And so what we need to do is in that pink or purple section that's entitled Optimum Zone, we need to operate within that zone. And that's, of course, easier said than done. But from a high-level overall perspective, that's the overall goal. How do we go about doing that? And how do we expand the width of that zone so that we're able to achieve all the emission requirements at the same time without compromise to the plant performance or certainly plant reliability? So now what I want to do is just talk a little bit more about some of these specific components. SCR in the United States, there actually aren't all that many units, coal-fired units left that do not have SCR. And it is coming, my understanding, to the Indian utilities. What I'm just showing you here is an overview. This is probably the most typical system where we have the SCR installed downstream of the economizer, upstream of the air heater in a vertical path here. And so there we have our SCR components, and then there's a cutout of what a SCR cube would look like. And if we go to the next
Mr.
slide.
Anthony, sorry to interrupt.
Yeah.
Sir, please share the screen, sir. The file is not visible right now.
Excuse me?
Sir, please open the presentation and share the screen of your laptop or desktop.
Oh, you mean you're, okay, I'm sorry. I thought you were seeing the screen. That's why I got the thumbs up. Sharing the screen here.
It is,
So it was visible in WebEx. It's just not visible on the live stream.
yeah.
Oh, okay. I apologize for that. So I would, how would I go about, okay, so under sharing the screen, let me do that. Okay, so if I do that, it is, how is that? Is it visible now?
Yes.
Okay, thank you. I apologize for that. I didn't realize.
Gaurav, is it okay now?
Okay. Excuse me?
Gaurav? Just a minute, sir. We are just...
It's visible now, sir.
Yeah.
Okay, thank you.
Now,
thank you so much.
Can you make it full screen,
so what
sir?
I'm showing you here, make it full screen. Okay, I will certainly do that. Okay. So this is the shown here the overall mechanism for how an SCR works, and from a just looking at the reactants and the products, it's very simple without looking at the intermediate reactions. You have the Knox coming in, and the reagent is typically ammonia, NH3. So the Knox and the ammonia combine, and what that leads to is basically water and nitrogen. Okay, and that's basically in the presence of a reactor how the system, how an SCR system works. Okay, so what we do at Effery within the program, what we spend a lot of time on is looking at the issues specific to improving the performance of an SCR system. Top of the list is fuel quality, and here again, I do note that in India, as SCRs are being seriously considered. The number one issue that we see is the very high levels of ash in Indian coals. Okay, in the United States, with our coals, we have a lot of problems with sulfur, with arsenic, leading to SCR catalyst poisoning. But ash, we believe, is going to be the number one issue when SCRs are installed with Indian coals. And the problem with ash is you basically mask the catalyst so that the reaction, the catalyst, if it's masked in ash, the reactants are compromised. Okay. Other issues that we're seeing is flexible operation, load changes. As you go down in load, the temperature to the SCR system also goes down. As the temperature goes down, that can create a reaction which deactivates the catalyst. Okay, ammonium disulfate deposition on the catalyst pores. Again, it's a deactivation mechanism. You also have high excess air and flow distribution problems. These are the challenges we see as we go to a flexible mode of operation for the SCR. And then finally, there are catalyst management issues. When do you replace the catalyst? You want to be able to do that during a planned outage. You do not want to take a unit down just to change a catalyst. So we have a software that we look at. We have different best practices we look at to enable operators to ensure that doesn't happen. Okay, and then finally, balancing Knox with So2 oxidation. Catalysts do a great job of lowering Knox, but unfortunately, they also do a good job of enhancing SO2 to SO3 oxidation, which creates problems downstream that we need to look at. And so these are just some of the issues that once an SCR is installed, even though SCR is considered commercial technology, these issues are still prevalent and we still need to deal with them. Another component of the environmental control train that I showed you in the overview slide is the electric static precipitator, or ESPs. Most of us are familiar with ESPs. Here is a very simple operation. Basically, we charge the particles, ash for the most part, just upstream of the ESP, and then they're collected on the plates, on the grounding plates, and then every once in a while those plates are shaken, and we call it wrapping, and then the ash is taken down into a bin and it's carried off. It's a relatively simple operation. They've been around a while. Again, high levels of ash mean that there are going to be some challenges with that. But my understanding is that one of the solutions that has been put forth, that have solved the issue certainly in India, in many plants, is just go with very large ESPs. And that's the more ash you have, the larger the ESP that you need. Looking here are some of the issues that we see with ESPs, and they're categorized into three areas. Upstream conditions, which again, changes in fuel quality is probably the biggest. If you have a fuel that's changing, you have what we call the resistivity of the ash going into the ESP may change, and that will change the performance, the collection efficiency of the ESP itself. So one has to be cognizant of that. Here in the States, we like to add chemicals to our flue gas to control metals. That may or may not happen sometime in the future in India. That creates more challenges for ESPs because in addition to removing the ash, one also has to remove the chemicals and dispose of the chemicals in a way that avoids leaching in the groundwater. And then, of course, as I mentioned previously, changes to upstream condition, excess air, temperature, distribution, all of this needs to be considered as the flexible operation or the change in fuel quality becomes prevalent. And then the other two, in the interest of time, I won't go over them in too much detail, but scheduled maintenance, best practices are needed for that. And then finally, electrical equipment related issues. To compensate for high resistivity ashes or fuels, we're looking at advanced power supplies, et cetera. So these are again issues that get back to the fuel quality and the challenges brought about by lowering the fuel quality to the environmental control system. I threw this slide in here for fabric filters is another way of controlling ash that is very popular in the United States. In fact, in the States, I'd say maybe 40% of all particulate control devices use fabric filters or bag houses as opposed to ESPs. India, not so much, but they're great devices. I mean, one way to think of a fabric filter might be, in very simplistic terms, a giant vacuum cleaner. Okay, that's pretty much what it is. The flue gas goes in, and you have these. If you look on the right, you see these. You see the various bags, and it almost looks like you're collecting the ash on the outside, depending on the design of the fabric filter, and of each of these bags. And you see a whole slew of bags in the main picture in the middle of the screen, and then the ashes stays on the outside, and the clean flue gas goes on the inside. Every once in a while, that you need to shake or you need to pulse the bag itself to remove that ash. And again, like an ESP, collect it in a bin and cart that off to your ground fill, or if you sell the ash to your point of sale. One of the challenges, one of the issues we're looking at here is bag life, materials. How can we get the materials of these filter bags to last longer so that we lower the maintenance requirements and we're able to keep the unit in operation? You certainly, just like you don't want to take a unit down to change your catalyst, your SCR catalyst, you certainly don't want to take a unit down to change your filter bags. Okay. The last topic I will cover is So2 control. And when we talk about So2 control, most people will say, well, okay, we need a wet flue gas desulfurization system. And the reason for that is there is nothing more efficient than a wet FGD. Now, shown here, though, in this table, that you can see that in many cases, you can get close to 99% removal efficiency of SO2 with a wet FGD system. However, wet FGD is the most expensive way of controlling SO2, and there are alternatives. So we like to work with our funders and say, well, if you need a wet FGD system, we'll work with you on that, and we'll ensure that the specifications of the FGD system are consistent with what your needs are. However, in many cases, significant savings if you go to an alternative approach, if you're able to do that with your fuel and your regulatory requirements. And the two listed here that I'll cover briefly are what we call the semi-dry processes, which can give you about 90–95% removal efficiency, and then sorbent injection, which can give you from 50 to, say, 70% removal efficiency. And we'll look at each one. We'll start out with the lowest cost method, which is injection of an alkali sorbent. Either hydrated lime is probably the most prevalent, that's calcium-based, or sodium-based sorbent is also used quite extensively in the United States. Trona is an example of a sodium-based sorbent. You can inject your sorbent in a number of places as shown here. You can do it in the furnace. You can do it in the economizer. Do it downstream of the economizer. It's basically the main issues we look for in sorbent injection to control, to do a better job is the efficiency. A sorbent injection system, the capital cost is relatively low. The expense is what you pay for the sorbent. So what we look for is ways of improving the mixing between the sorbent and the flue gas, and in doing so, we can get maximum reduction in SO2 in a way that minimizes the amount of sorbent that's needed. Okay. So the system that's in between the lowest cost and the highest cost are what I call semi-dry processes. Here's an example of one. This is what we call a spray dryer. And basically what you have here, you're using lime, calcium-based, okay, component, and you're liquefying that. You're doing that in the flue gas, that gets injected in the flue gas stream. And then you're capturing, you need to capture that line prior to certainly going to the stack. So in a fabric filter or an ESP, okay? And then that's captured and that's recycled, creating lime water. Now the ash is taken out. There's a drying process for the ash, and that can be disposed of. But then you're recycling most of that lime water, and that's been used on occasion. I think in the States, I'm going to say maybe there's about 10 to 20 applications of semi-dry processes, not necessarily spray dryer, but semi-dry processes. Okay, and that takes us to the wet FGD. And what I'm showing you here, this is a busy slide. I have a few more that maybe are easier to read. But this is showing the main components of the wet FGD system. You see going into the wet FGD on the left, you see you have your flue gas containing the SO2, and that is in a vertical cylindrical wet FGD system. That rises, and then coming down from the top would be your slurry, and that slurry is generated in the pond, if you will, at the bottom of the wet FGD, and that is containing your lime or limestone mixed in a fluid stream that is through the slurry pumps brought up through the injection nozzle and using atomizers sprayed into the system.
Mr. Anthony, you please finish in a couple of minutes.
Oh yeah, I'm done. This is my last slide. Okay, shown here at the bottom is the general mechanism. You see there's two approaches. One is inhibited oxidation. One is forced oxidation. The forced oxidation will generate limestone, and the limestone can be sold. Okay, so here is a picture showing the components surrounding the ESP. Okay, what we're seeing here is how the reagent on the left is prepared and injected into the wet FGD system, and then on the right we see how the water is taken to the water treating system and how the ash is then disposed. Okay, and just listed here, and this is the last slide, it just shows the issues that, some of the issues that we find with wet FGDs. One of the areas of big concern now is limestone. Limestone is a key component. It's very expensive. The use of the limestone is very expensive for FGD. So a lot of plants are looking at lower cost limestone. Unfortunately, lower cost limestone does give issues with the performance of the ESP. Other areas certainly looking at flexible operation. We do see quite a bit of issues at lower loads in operating the FGD system. And then as John mentioned, I unfortunately don't have time to get into it, is issues associated with FGD materials, okay? And with that, I believe that is the end of my presentation.
Thank you, Mr. Anthony Facchiano. I think the topic which you dwelt on is a very, very relevant topic to India today. In our power sector, we are going in a big way for Knox and SOx control. Particulate matter control is something which we have been doing. And Indian coal has a very high ash content, so our ESPs are pretty big, as you rightly said. But we have been doing it effectively, particulate control. But Knox and SOx, yes, we have just started. And for Knox control, you have very rightly said, for us it is a staged combustion. And whatever experience we have till date, we are not facing much of a problem. But then when we operate for a longer duration, we will have to look for whether there are any signs of fireside corrosion. High LOI is not a matter of concern for us at present. CO also is under control so far. So that is not a concern for us. Post-combustion NOx control SCR technology for high ash content Indian coal is very difficult. We perceive it will be very difficult for us. And particularly when we use it along with flexibilization, when we go down on load, it will become difficult. So that is why that will be a big challenge for us. Dry, wet FGD is the one which we are going in a big way. In some cases, we are going for dry sorbent injection. You have very rightly focused that in dry sorbent injection, the capital cost is less, but the variable cost will be more because we will be using, we'll have to use a raw material. So that cost will be, has to be paid by the consumer. So, and fabric filter, in India, we have at some place, a hybrid ESP. We have a fabric filter and a conventional ESP. And the challenge with fabric filter, what we as utilities in India have faced is, when we use, times we have to use oil guns sometimes, even in the running condition. So during that time, there are issues with respect to the high DP of the fabric filters. So thank you very much for enlightening the entire audience about all the environment mitigation technologies. You have very rightly said earlier it was only clean air. Now, of course, it is clean landfill and clean water also. Thank you once again. So now we go over to the next presentation. This presentation will be by Dr. Andrew Maxson, and he will be speaking on carbon capture and storage and the energy storage. Dr. Maxson is a program manager at the Electrical Power Research Institute. He is responsible for EPRI's Industrial Technology Demonstration Program in the generation sector. He is working on two important components for potential CO2 reductions, carbon capture and storage for fossil-fuel power plants. And the current demonstration project in which he is involved includes post-combustion, CCS, integrated gasification combined cycle. And I think prior to being associated with EPRI, he was at General Electric. So I welcome you to make the presentation. Over to you.
Hello? Can anyone hear me?
Dr. Andrew, you please start the presentation.
I've started the presentation.
Yes, please. You start.
Can you hear me?
Yes, sir. The voice is little feeble, sir.
Can you see my presentation?
Yes, we can see your presentation, sir.
Okay, thank you. Well, thank you much for the introduction. I have done a lot in carbon capture and storage in my career, but I will not be talking about that. My colleague, Abhoyjit Bhown, will be talking about that after I'm done with my presentation, where I'm going to talk about energy storage and its potential integration with thermal power plants. So the need for energy storage is changing throughout the world, including India, as more and more variable renewable energy, so wind and solar, gets put on the grid. The reliability of the grid becomes less and less. Dispatchable resources like coal start to get operated more flexibly or shut down. And energy storage needs to rise up to fill that void when the wind doesn't blow or the sun doesn't shine. In today's world right now, most of that at a larger scale is being provided by lithium-ion batteries. Lithium-ion batteries have some limitations, as I'll talk about in a second. For one thing, they typically have shorter durations in terms of how much energy they can provide, and typically they're relatively small on a grid basis. So right now in India, the amount of variable renewable energy is about 8% by energy, and it's almost 20% by capacity, but it's projected to grow dramatically. In fact, there are very aggressive goals to grow solar and rooftop solar in India, and ultimately the capacity of renewable energy is going to be planned to be 60% by 2027, and most of that growth will be solar and wind. So in tomorrow's world, there will be a lot more of these intermittent resources, which their intermittency can cause stability issues on the grid. You need to be covered with more and more storage that needs to be larger and longer duration. And batteries struggle for longer duration of 4 hours because the cost of batteries goes up dramatically as you go to longer durations. So as you get into that need to go beyond 4 hours all the way out to several days worth of storage, which is projected to be needed once you get past variable renewable energy in the 30 to 40% range, you're going to need 8, 10, 12, up to 24, maybe even 48 hours worth of energy storage. And batteries will be very expensive. They have other issues. They take up a lot of footprint. They have safety issues. And another issue is they don't provide any real system inertia because they don't involve a rotating asset. And at some point, when you're displacing your coal plants, which are still producing almost 60% of the power in India, with assets that don't have any real system inertia, you're going to be inertia limiting. So having energy storage that can provide synchronous generation will be of growing importance in India. When you go out to future goals, out to 2040, 2050, where many regions in the world are projecting to go towards very low carbon, India may be a little less aggressive on this because of their reliance on coal. But when you get significant amounts of renewable energy on the grid, you're going to need energy storage that's even longer than a couple of days. And when you move in that space, you're going to need a fuel to be able to provide that energy storage for longer periods, even up to seasonal. And many people are looking at hydrogen and ammonia and other low-carbon fuels for that. So a key to what I'm going to talk about is trying to come up with lower-cost bulk energy storage, and in particular, if it can take advantage of the huge fleet of coal power plants that are in India to reduce costs and maintain those rotating assets. So these are the different types of energy storage. This should be clear to everyone, but chemical energy storage is things like a fuel, like a hydrogen. Electrochemical are batteries, like lithium-ion batteries, and actually there is a lot of potential battery installations ongoing in India, including a projected 10 gigawatt hour, which would be the largest battery in the world if it does get built. There are mechanical types of energy storage that include pumped hydro and compressed air energy storage. There's quite a bit of hydro in India, but the issue with mechanical forms like pumped hydro and compressed air energy storage is they're geographically limited. You need the right geology for them to be employed, and much of the pumped hydro opportunities have already been used in India, and finding the space and geology for compressed air energy storage has been a challenge. So another form is thermal energy storage, which is basically heating a bulk media and then recovering that heat by changing a little working fluid. This is a form of energy storage which can be quite large. This is a chart that shows duration of energy storage versus the amount of output. On here you'll see a bunch of batteries, including the largest battery in the world, which is actually in Australia right now, about 100 megawatt hours. But if you're going to need large amounts of power and longer duration, pumped hydro really serves that right now in the world. But with the ability for it to grow being limited, you can see that here's a pumped hydro site that's 300 times the size of the largest battery right now. But in this area where you need larger scale and longer duration energy storage, thermal energy storage really will have some play, particularly since it can integrate with coal and gas. So it is very cross-cutting. It can be used like combined heat and power, where you can take heat from anything that can provide it. That could be coal, that could be gas, that could be concentrated solar, it can be nuclear. It can even be solar PV and wind if you convert this electricity into heat. And this is actually happening in some places in the world. It's not particularly efficient, but it can be done very low cost. You convert this to heat, you can store the heat in a variety of different systems, and then convert that back to a working fluid, which is typically steam. It can also be air, it can also be supercritical CO2 to produce electricity, and you can also use that working fluid to produce heat. So the system is very flexible and something that most power plant engineers would all understand because the systems will look familiar. So here's a potential deployment of thermal energy storage where you have a coal power plant that has been pressed by renewables to no longer operate at where it was designed at base load. It's now operating at a much lower capacity factor. So the intermittency caused by low-cost renewables require this plant to start up and shut down often, ramp, have higher maintenance costs, shorter lifetime, and higher emissions on a per megawatt hour basis. So it's just not running the way that it was designed to, and it becomes very expensive and inefficient. So if you take several of these units and take them offline and decommission them, but keep the steam island still in place, you can install thermal energy storage and keep one of the units operating, which will now operate more like a base-loaded unit at high capacity factor. It will operate all the time, and when power is needed on the grid, it will be put on the grid. When it's not, it will be charging this thermal energy storage system. But then when it operates, you actually now have something that looks like a peaker plant where it's driving the steam islands from the decommissioned units, and the coal plant is still operating. So Effery has done a lot of work on this. This can be extremely cost effective. The cost of storage is about 1/4 to 1/6 the cost of a standalone battery. And the benefits of integration in terms of improving how coal is used in the country are significant. Over time, if this coal has to go away because you need to continue to lower carbon, this can then get heat from renewables, from solar and wind, through an electrical heater, which it won't be nearly as efficient. Typically, these are 80 to 90% efficient when you're using heat from a power plant. When you convert it from renewables, it drops to about 30%. But the costs are dirt cheap because you already have this in place and it's using existing equipment. So here are some examples of thermal energy storage systems which are being advanced. Most of them use a cheaper storage medium. The molten salt system is the only commercial one, and this uses a thermal media, which is very expensive, molten salt, thousands of dollars per ton. Trying to replace that with something like concrete or sand or gravel, which are much cheaper, much more prevalent, dramatically reduces the cost. So Effery has been doing work on concrete thermal energy storage, sand, which gets blown around through a heat exchanger, a fluidized bed heat exchanger. We've also looked at pumped heat energy storage, which uses thermal energy storage as part of it, but has a standalone power cycle in it, which is reversible, that either creates heat by compression to be stored in these cycles, or takes that heat to rotate a turbine to generate power. These are standalone AC to AC direct competitors to a battery, and have real inertia and will be cheaper and smaller footprint, and liquid air energy storage, which has some analogies to compressed air energy storage, except that you store the air not compressed underground in the gaseous phase, above ground in liquid phase, so that you're not geographically limited. So just quickly, one of the projects that is being advanced to be commercially ready by about 2027 is concrete thermal energy storage. It's a very simple system where you have concrete blocks that are laid down that have steam or another working fluid running through them to heat them up, and then water or another working fluid running through them to take the heat when you want to generate power. The material is very cheap. It's very prevalent, so there will never be shortages of it, unlike lithium, which might have shortages for batteries. You're never going to run out of concrete. And this design with the coiling has been shown to avoid the thermal cracking from the different expansion rates of the metals and the concrete. So concrete has been very durable for thousands of years. The Romans invented it, and there's a picture of Pantheon. It's still standing after 2,000 years. There's no moving parts. It's completely transportable, so it's relatively simple to install and operate. And because these can be stacked, it's a pretty small footprint. So this is a project that EPRI is working on where we're testing a 10 megawatt hour scale system. This would be using commercial blocks. There's actually 54 of them required to make 10 megawatt hours. So if you want to go to 100 megawatt hours or a gigawatt hour, you just add more and more blocks, so that scaling up to do longer and larger durations is very cheap, because you're basically only adding concrete and piping. So we're hoping to have this operational here in the next 6 months, and then we're going to do 8 months of testing to validate the technology and have it be ready for commercial use in time for this 2030 timeframe, where people are thinking that they're going to need a lot of energy storage. It's going to need to be cheaper and more flexible for a low carbon future. So with that, I'll stop and turn it over to my colleague, Dr. Bhown.
Thank you, Dr. Andrew Maxson. I think you have given very good presentation on the energy storage facilities which will be available in years to come. At present, as you rightly said, we are focusing on lithium-ion batteries, but for a bigger scale of storage, larger scale of storage, I think we need thermal energy storage. We already have the molten salt molten salt storage available in thermal energy storage commercial units. I think that is already available commercially. You have talked about the concrete TES. You have also talked about liquid air energy storage. So I think you have given us a glimpse of the future. when the future will be like this, maybe by 2030, 2050, all these storage technologies will be very mature, and these technologies will be helping us integrate more and more RE and provide stability to the grid. Thank you very much for providing the insight to all the delegates. And now we will come to the final presentation of the session. And I think this presentation will focus on carbon capture and storage. Our speaker will be Dr. Abhoyjit, and he is the program manager for carbon capture and storage at Electrical Power Research Institute. And he and his group of engineers and scientists, they are focusing on reducing the cost and decreasing the risk associated with carbon capture and storage. I think the risk essentially is about leakage of carbon dioxide probably. And he has roughly 30 years of experience in development of separation technologies across wide-ranging industries. So I welcome you, Dr. Abhoyjit. Over to you. You can start your presentation.
Is my screen and voice okay? Is it visible?
Yes, it is okay. Yeah.
Good. Namaskar. My name is Abhoyjit. I'm the program manager, and I lead the carbon capture and storage program here at EPRI. I thought I'd start this talk looking at the global emissions and energy picture. And I think that probably most people are aware of the current situation about anthropogenic greenhouse gas emissions. Globally, roughly we're emitting about 55 gigatons per year in 2018. 37.5 gigatons of that is CO2 from fossil. And if you take a look at these plots, essentially you'll see that the every year we have higher and higher emissions, so record emissions are continuing, and that there's no sign of peaking those emissions. And if you take a look at the, sorry, I'm going to turn off that. Yeah, if you take a look at the target requirements we have for climate change mitigation, the targets are that by 2030, we need to reduce our emissions by 25%. And by 2050, we need to reduce it by 67% in order to meet our 2-degree climate goals. So the future is really not that far off. It is really upon us and has been upon us for a while. If you're looking at 1.5 degree scenario, you're looking at reducing emissions by 55% by 2030 and 90% by 2050. So given the last, let's say, 20, 30, 40 years of trajectory, it's really difficult to see how this can be managed without some drastic changes. And those drastic changes, again, are not in the distant future. They really are upon us. The reason why this is, of course, happening is because our primary energy consumption is driven by fossil fuels. This is the picture of the total world energy consumption in units of cubic miles of oil. So rather than thinking about barrels of oil, you can consider a cubic mile of oil, and you can project that energy units into different kinds of energy. But if you take a look at this picture, you'll see that oil, coal, and natural gas, this comprises the overwhelming majority of energy consumed in the world. These other forms of energy are less. Solar and wind and renewables are making very important and very good strides, but it's not yet been enough to contribute significantly to global CO2 reductions as much as what's needed here. And in fact, if you take a look at the units, the amount of energy being used in the last, say, 12 years, the energy consumption over this time period went up by 25%, but and by that I mean that the energy consumption today is around 4 cubic miles of oil, Before in 2006, it was 3.2. So the energy consumption for the world went up 25%. But interestingly, that the market share for fossil fuels, the amount of energy we use from fossil fuels, really remained unchanged. It's roughly 80%. And so what that means is that the growth in energy, which we saw here, was still overwhelmingly supplied by fossil fuels. And what this means is that globally, that fossil consumption is outpacing our energy decarbonization efforts. And so if you look at the next 10 years compared to the previous 12 years, it's really difficult to see how these things could be managed given our past trajectory. If you take a look at emissions by country, this is a plot of essentially those tons of CO2 emissions by year. China has been emitting more, and currently it's the largest emitter. United States is second here. The EU as a bloc is fourth, but India as a country is the third largest emitter. And projections are, of course, India's CO2 emissions will continue to grow as the economy expands. So in the face of an economic expansion, as well as energy needs for India, it's critically important that CO2 emissions be managed. Of course, per capita emissions for India are quite low still compared to the US and China and even the world average. But nonetheless, that India as a country does need to look at CO2 emissions. And so if you take a look at the emissions from CO2, emissions of CO2 from the power sector, it's around 900 or maybe slightly more than 900 million metric tons a year. This was as of December of 2018. I didn't get a chance to look at more recent numbers. But let's just say it's about slightly less than 1 gigaton from just the power sector. As a country, it emits around 3 gigatons. Onshore storage, if you take a look at carbon capture, and then you have to do something with it. So if you look at onshore storage, there's very wide-ranging estimates for how much CO2 could be stored onshore. Subsurface is anywhere between 75 to 525 gigatons. Offshore is even larger, in the hundreds of gigatons to thousands, a couple of thousand gigatons. So the point I was trying to make here is that at least in potential, that there's a reasonable amount of CO2 storage available in India relative to emissions from the power sector. So what exactly is CO2 capture and storage on fossil power? I won't spend much time on this slide because I assume most people are familiar with at least post-combustion, in which you take coal and or any kind of fossil fuel, and you do a separation of CO2 from predominantly nitrogen, and then the CO2 is separated and you can compress and dehydrate it. You can also do pre-combustion capture, in which you do gasification followed by water gas shift and do a CO2 hydrogen separation to get out CO2. And then oxy-fuel combustion is where you separate air, essentially oxygen, nitrogen, and you combust a fuel in a pure oxygen or mostly oxygen stream. And in all these approaches, there's a separation step involved, and that really is the driver for the cost and energy involved in CO2 capture and storage. But once you have the CO2 separated, you can compress it and dehydrate it, and typically you're going to inject it into aquifers of some kind, which are subsurface, which is the capacity I mentioned in the previous slide. And what that looks like, at least in the case of a post-combustion process, is just like you have a boiler followed by SCR and electrostatic precipitators and now FGDs. The thought is to put in essentially an additional environmental control unit here, which is CO2 capture. In the case of coal, CO2 is about 12 to 15%. When you have a natural gas combined cycle, it's 3 to 4% or so. In some cases, it's advantageous to recycle the CO2 back to increase its concentration so that capturing CO2 is easier. But this block here, essentially of the CO2 capture, is can be thought of. Let me get some pointers here. Yeah, so this block here of the CO2 capture block is really just another environmental control, and that has to do with a solvent-based system in which you have a CO2 selective solvent which will absorb the CO2, and then you have to remove the CO2 by heating it up. And the heat for this thing actually is delivered from the power plant steam cycle. An adsorbent, a solid sorbent, works very similarly, in which you can have a solid particle absorbing the CO2, and again you have to heat it up from the power plant. And a membrane system which works on a pressure differential. So if you were to apply a pressure differential across this membrane, then the CO2 could selectively permeate. And again, the power needed for that pressure differential comes from the power plant. So in all approaches to CO2 capture, you're going to have some impact on the power plant. And that is really the crux of the CO2 capture problem. But it's really not a problem when you look at the global picture, because why do you want to do this? The Intergovernmental Panel on Climate Change basically has estimated that climate change mitigation will be 2 times more expensive if people don't have access to CCS. And this is because it really is a needed as a low-cost option to meet the climate targets, which I had mentioned in the first slide. But the question is, what happens when you get the CO2 captured? Then what can you do with it? One option is to look at chemical conversion, if you can convert CO2 into something. But not generally, but essentially all of the CO2 emissions which the world emits is by far larger than any carbon used by the entire chemical industry. And so even if you were to convert all the CO2 into something, some kind of chemical, there's going to be vastly more CO2 emissions from the world. So there is very limited opportunity here of converting CO2, but there can be niche opportunities depending on the area. There's an opportunity to convert CO2 back up to a fuel, of course, but that's a thermodynamically uphill process. But it is a fairly large market, but obviously we need to have CO2-free energy sources to make this pump go uphill. But then the question is, if such sources are available, then it's probably better just to reduce fossil and then use a CO2-free energy source directly, particularly when you look at energy storage. And so therefore, there's limited opportunity here as well. The one option you have when you're looking at CO2 is you can do enhanced oil recovery, in which you inject the CO2 to get out more oil from the ground. And there's actually a net benefit from that potentially as well, depending on the reservoir characteristics. So there's a net CO2 reduced into the environment. And India does not do a tremendous amount of EOR, and there's certainly literature suggestions that opportunities do exist for enhanced oil recovery, but certainly more work needs to be done in this area. The biggest option is geological storage. And as I indicated earlier, capacity estimates vary widely in India. One of the challenges is that one has to do sourcing matching, of course, look at public policy, technical hurdles, and acceptance by the public will definitely reduce the numbers which I showed you earlier. But nonetheless, there's probably going to be tens to maybe hundreds of years of storage capacity in India. But if you look at the entire picture, CCS really is the only major option for reducing emissions from fossil fuel. There really is no other option if fossil fuels are going to be continuing to play a role in the energy mix. Since I was asked to talk about the latest trends in CCS, I thought I'd show you some recent work from the Global CCS Institute in Australia. This is a map of all the projects that there of CCS. There's 51 in the world. 19 are operating, 4 under construction, 10 in advanced development, and 18 are early development. And there's actually a CCS operation in India itself. This is a company called Carbon Clean Solutions, which is based both in India as well as the UK. It's running a CO2 capture system on a 10 megawatt slipstream flue gas from a coal-fired power plant outside of Chennai. And the CO2 in this case is not sequestered underground, but it's actually used to convert to soda ash. So there is enough of a market there at the small scales for this process to be economical. And I believe this was started up, I think, 3 or 4 years ago. So India is certainly active in the CCS space as well. But in terms of large-scale reductions, more work needs to be done. If you take a look at what kinds of projects these are, these tend to be across many different industries, things like waste incineration to cement, chemical production. Natural gas processing is a very large area where CCS has been operating. And this is not a new technology. This has been around for at least since the 1930s, so close to 100 years now. A lot of that has been applied towards the natural gas processing area. Power generation, the red ones here are the ones in operation, and there's only two in operation. One's in Boundary Dam, which is in Canada. And this is about maybe roughly 100 megawatts of the equivalent slipstream. This is the power plant itself, and this actually is the capture system. And again, this is a very small fraction of the total power plant output, but this gives you an idea of scale of these systems. The CO2 in this case is captured and it's sent to oil field about 100 miles away for enhanced oil recovery. The second one in the world is actually in Texas here in the U.S., and this is Petranova. And in this case, it's the same idea that you're capturing CO2. In this case, it's about a 250 megawatts stream out of the power plant, and the CO2 in this case is again captured and sent by about 100 miles again to an oil field in Texas. I should mention that literally just a few weeks ago, this particular site for CO2 capture was suspended temporarily because of the low oil prices. Presumably, if the oil prices are back up, then this process will come back online. At the moment, in the world, there's only one currently operating at large-scale power plants. And so at EPRI, what we do is, of course, we do monitor and track all these large-scale developments. But equally importantly, we do a lot of work in the research side. We actually have databases for our members on both CO2 capture and storage. And we also have a database on novel cycles. So these are essentially ways to generate power from fossil fuel sources using different power cycles. And so we have actively maintained databases on these for our members. And here's an example of a post-combustion CO2 capture database in which we have listed, I think, probably about 50 or 60 of these technologies. And one can click on this and get an example 3 to 5 page write-up as a good idea of what the technology is doing. Some recent data, which I can just show you as a histogram, that there's many different kinds of technologies being pursued in the research stages from early stage here to very late stage here, and involve things like solvent or absorption, solid adsorption, membrane systems, and other. You'll see at the larger ones, only the solid ones are present, which is typically an aqueous amine solution. But there's a lot of work going on in the R&D space on different kinds of approaches for CO2 capture. And EPRI is heavily involved from very early stage research all the way to late stage research in a variety of these technologies in our research program. I just wanted to mention the cost, because that's a big driver, of course. If you take a look at combustion CCS on a supercritical coal plant and a natural gas combined cycle plant, CO2 concentration, as you know, is 12 to 15% here and 3 to 4% here. And if you take a look at the cost for CO2 capture and compression and storage, it's about $46 per ton for a coal plant, and it's about $80 per ton for an NGCC plant. The levelized cost of electricity actually goes up. It goes up about 77% for a coal case and about 72% for an NGCC case. A lot of the research which we and other people around the world are pursuing for this is to reduce cost of CCS, primarily these costs. And Mr. Gupta is absolutely correct that the mitigation here is looking at reducing the mitigation of CO2 leakage and from subsurface reservoirs. and groundwater contamination as well. I should mention that those are fairly well understood processes, but certainly large-scale injection needs to be done in the world. Here's a breakdown of the costs. Here's a subcritical without CCS and with CCS, supercritical without CCS and with, and here's an NGCC with and without CCS. So my last closing comments is that approximately 80% of the world's energy comes from fossil fuel. They're unlikely to be displaced in the next few decades, which is the time frame we have to deal with this climate change problem. And really, CCS is the only option, at least for fossil fuels. If you look at broader studies, certainly CCS is key to a low-cost pathway to mitigating climate change. And it requires collaborative work. It's certainly not a commercial technology at wide scale for power plants. Again, there's literally only one operating in the world today. So getting this technology deployed will require collaborative work, not just within a discipline, but equally across chemists, engineers, power plant generators, and geoscientists. I am from India. I'm actually from Rajasthan. And I've been watching a lot of the events, of course, unfold in the world. And I was actually very much struck by the change in air quality across India because of the shutdown. And I'm often reminded that people complain about the cost of having clean air and water. And I just want to show this slide, which basically asks the question, is it really too expensive? And I was impressed again by the changes going on in the country. So thank you very much. And I'll be pausing here and turn it back to you, Mr. Gupta.
Thank you, Dr. Abhoyjit. And we were all also very pleased to know that your origins are from Rajasthan. So carbon capture and storage, you have very rightly said that apparently in the coming 2-3 decades, it doesn't appear that fossil fuels will not be playing a major role in the power sector. And if they continue to play the major role, CO2 capture is going to be very, very important because world cannot miss that 2 degrees centigrade target. We cannot afford to miss that target because that is going to bring, that climate change is going to cause havoc for us. Already we are seeing across the world, the climate is only undergoing a big change, leading to floods, leading to cyclones, leading to drought, heavy rains. The pattern everywhere has changed. So you have given us an insight into the CO2 capture, the post-combustion, the pre-combustion, either through solvent or through adsorbent or through membranes. Geological storage appears to be the option today. The only problem with countries like India is the cost. We want to give affordable electricity to our people so that their dream of a quality life is fulfilled. And CO2 capture today is going to increase the cost, almost double the cost. If you see the levelized cost, it is 70%, 80%. And that too, the technology we have to get from most of the advanced countries. All the same, it was a very insightful presentation from you. So I think we have come to the end of a very, very informative session from the Electric Power Research Institute, from topics varying from flexible operations to emission control to material selection to energy storage and carbon capture. Mehul, I think we are already late.
Yes, sir.
Can you take a couple of questions from the chat box?
Yes, sir. I'll just read it out, sir. I hope you can hear me.
Yeah, I can hear you.
Yeah. So there's a question which is there any study in progress for operating 660/800 megawatt units with below 30% load continuously without sacrificing any unit parameters? I think this question is for Mr. Stephen Storm.
Yeah, so I can answer that question. So there's many units that are operating under 30% capacity factor. And for example, last year, one recipient of a tech transfer award of a utility that applied this systematic approach to min load reduction and flexible operation was at Duke Energy. And they had demonstrated and have continued to demonstrate ability to operate as low as 10 to 15% capacity factors on a regular basis.
Okay. Thank you. Thank you, sir. I have another question. Just a minute. Yeah. There's a question to Mr. Anthony. How to address issues related to rubber lining in wet FGD? Hello? Mr. Anthony, you're on mute.
Mr. Anthony, you unmute yourself. Your voice we are not able to hear. I think Mehul is speaking, but we are not able to hear.
Yeah. Gaurav,
can Stephen help? Storm, can you help communicating to Mr. Anthony?
Yeah.
Please try. Please try.
I'll send him a text. Can you go to the next question and I'll send.
Okay. Okay. I think again the next question is also to Mr. Anthony only. It is how to tackle the issues related to high DP across GGH and wet type FGD. Those are the three questions actually.
Can you hear me now?
Yeah.
Did you? Okay, but did Steve answer the question though?
Mehul, repeat the question. Mehul, repeat the question.
Yeah, there are two questions to you, sir. Mr. Anthony, there are two questions for you. One is how do you handle the issues related to wet rubber lining in FGD? In wet FGD?
Wet global lining. Yeah, I am going to. There was a. Let me just take that one first because the liners. We did have problems that were brought up by Dr. Shingledecker, who I assume is on the phone. We had a very extensive collaborative study between the environmental control and material groups, and the issues were with one specific material, 2205, which we worked with the vendors to resolve. If that is the question that's being asked, who was very involved in that was John Shingledecker, and I will ask him to provide more details. But first, I want to know, is that what you're referring to?
So, no, that's the only thing mentioned there, sir. The question just states issues related to rubber lining in wet FGD. That's all.
Sure. I can address briefly. Most of the issues related to rubber is in the application itself, and it's still even with the metallic vessels used in a lot of pumps, and not all. There's a number of different, let's just say, different varieties of rubber that you can use in the pumps, but they tend to be problems. They tend to be problem area because they end up clogging up pumps and eventually breaking off. So there's been a lot of switch due to erosion of removing rubbers or changing to different, harder materials in the pumps themselves. So there are issues, and there's a lot of experience with rubber linings, mainly in the area of things like pumps.
Okay. Okay. There is another question, last question. How to tackle the issue of high DP across GGH and wet type FGD?
I'm not quite sure. I'm sorry, I didn't hear the question.
Yeah.
Is this also an FGD question?
Yes, I'll repeat again. How to tackle the issue of high differential pressure across gas heater in wet type of FGD?
Okay. Well, we haven't seen too much of that. The high differential pressure across. Is this at the top loads, or you're talking across the differential pressure of the flue gas? Is that the
Yes.
Is that the question?
Yes.
Yeah, we haven't seen too much of that. What the obvious way is lowering the excess air. Is this a particular plant you're referring to? And if we have seen this, I'm not familiar with this being a tremendous issue. But again, other than lowering the excess air, I'm not sure. How. Again, I'm not sure. I'm not familiar with this issue. Okay.
Tony.
Mehul, I think this question is from NTPC Vindhyachal, if I'm not mistaken. So
yes.
I would request them to put it in a mail. Mehul, we will have to have a concept that the participants can ask the questions in the mail so that the speakers can answer later on also.
Yes, sir. We will do that, sir.
Yeah, I agree.
Yeah.
This sounds like site-specific issue that we'll be more than happy to help you with. I think an email would be the way to do it. If we can ask the particulars, and then we may be able to offer some advice. I agree with that. Yes.
Yeah. Okay.
So one comment on that is with Indian power stations having such high erosion rates, one thing to be taken consideration is air and leakage. And so when we commissioned a lot of FGDs, several of the initial designs that were implemented in the U.S. Did not account for an extra 20-30% flue gas volume that was coming from air and leakage on the system. And so this is something that needs to be taken care of in regards to how it impacts ESP efficiency to be able to mitigate heavy ash carryover to the FGD, as well as taking into account the flue gas volume. So these are areas that you should have in your defense strategy when looking at how you address that from a holistic strategy.
I think very correct, Stephen, very correct. Storm, I think maybe one visit to Vindhyachal plant from your side will be overdue, and then we can look at the exact problem. Meanwhile, I think Vindhyachal can send a mail to Dr. Antonio, and CII, please enable that the delegates can ask the questions through email.
So all the delegates can send in the questions to us. We will be more than happy to share it with the EPRI team, and they can come back on that.
So Mehul, I think now it's already past 8 p.m. I think it's time to thank all our brilliant speakers from EPRI who have enlightened all the delegates well in the different areas of flexibilization, for emission control, for carbon capture, for energy storage, and for material selection. I think it has been a very, very informative session. So thank you once again to all speakers from Effery. Thank you to all the participants and delegates for their tenacity, and thank you to CII for making this happen. So I think I can say good night to my delegates from India, and probably good afternoon to all from Effery. So thank you. Have a fantastic day. Thank you.
Yeah, one small announcement. Tomorrow we start at 12 o'clock. We have another interesting session lined up from companies from Japan. So please join us there. Thank you. And all the participants, please visit the exposition center. There are a lot of interesting companies there as well. Thank you. Thank you, sir.
Thank you. Thank you.
Thank you, Alok Gupta, sir.
Thank you.
Thank you, speakers. Thank you for joining us.